You want to do a sound check?
Okay, we have another adjourned number.
Who is it?
Test. Hi, Steve. Can you hear me?
Yep.
You need to go to the Zoom link first. Yeah, Yuri's just sent an email for this.
Okay.
Okay. See you.
See you.
It's in the US. He's quite tired. It's a bit early in the US right now. Hmm? Is it recording? Is it recording? Is it recording?
Just a moment, sorry. I'm nervous. Okay, welcome. Take a seat. So just to introduce myself up front, for those of you, I'm Joris van der Vondel from the Department of Physics, the same department, but from the condensed matter section. And I'm today the chairman of this session. Okay, so just before we start, I think Steve, Lucas, and Claudio are well connected and they hear us loud and clear, just to be sure. Yep, okay, thanks. Okay, then let's start with the opening. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. I hereby formally open this session and I welcome you all to the public defense of Germain Garreau. Germain Garreau has presented to the faculty the PhD thesis on the topic nulling interferometry from exozodiacal dust with the LBTI to exoplanets with Asgard NOTT at the VLTI. In parallel, in partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy, and astrophysics. Germain Garreau shall now publicly defend the PhD thesis Germain, Garreau, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I now give the floor to Germain Garreau.
Thank you. Everyone can hear me? Yes. Okay. Thank you everyone for coming. I know last week was quite a lot with 3 defenses, so I really appreciate that you took the time to come here for yet another defense, and especially thank you for the people who traveled a lot to come here. So indeed, today I will present the topic of my thesis, nulling interferometry, etc. So typically what people do is that they start by presenting the key words in their title, which I will not do. And instead, I want to give a bit more context about like the topic of studying planetary system, because this is all about this defense. And I want to start with a picture I really appreciate. That's not the picture. So in 1990s, the Voyager 1 spacecraft was starting to leave the solar system. It was like getting outside the orbit of Neptune. And people asked NASA to turn around the spacecraft and start to take a family picture of the solar system, which it did, and it gave a few snapshots of the solar system with all the planets of the solar system at the same time. You can see Jupiter, you can see Earth, the pale blue dot that Carl Sagan is talking about, Venus, Saturn, Neptune, and the planet whose name shall not be said in English. So I really appreciate these pictures because this is the kind of picture that we also get when you observe other stars in the universe and the planetary system that is orbiting around. So we know now that planet exists outside the solar system. You can see a famous example with the HR 8799 system and its famous 4 young giant planets orbiting around. But actually, we have not only discovered exoplanets around other stars, we have discovered like complex systems with comets, dust, like Kuiper belts, like asteroid belts, of course, planets. So we realized that planetary systems outside our solar system are actually quite complex. So the question is, how do we manage to study them? How do we manage to get a complete pictures of these complex systems? So for this, we use what I like to call a mosaic of techniques, of different techniques that are mainly used for planets, but not only for planets. You have transit, microlensing, astrometry, direct imaging, and the one that Jake presented last week, radial velocity. In the context of this thesis, I will focus on the technique of direct imaging, but I should say the techniques of direct imaging because there are several of them. So they all share the same advantage, let's say, that is that they are able to separate the light from the star and the light from the planetary system or the planet. So here you have a couple of famous examples. You have 2 images of planets at the top with AB peak A and B, and the one where I will not say the name. And you have a famous also image of the beta peak system that was taken by the NIRCam and MIRI camera on board of the James Webb Space Telescope, where they are imaging not a planet, but you see a debris disk that is around the forming star of beta peak, well, the forming planetary system. So that's very nice. Direct imaging is very interesting because then you can directly detect the light from the planet or from the planetary system, and then you can do long observations, like typically a few hours. So you can get a lot of signal-to-noise ratio of this system, which allows for an extensive study of these planetary systems. There are, of course, a few drawbacks. Otherwise, this would be the only method that we use for a planetary system observation. It's quite a slow cadence type of observation. So it means that you can only observe one target per observation. You cannot do a full sky survey with direct imaging, which means that large surveys requires a lot of exposure time, lots of time. It also requires a good sensitivity and a good stability, especially when you need to do high contrast imaging, when you want to observe faint planets. So talking about high contrast imaging, we have several techniques available. The main one is coronagraphy. That is like the main one used to observe planetary system and planets. But recently, in the last decades, interferometry has started to be used, especially optical interferometry has been used to observe planets and planetary system, especially with the gravity instrument at the VLTI. And here in this thesis, we're talking about nulling interferometry, that is a mode of interferometry that we want to use for observing planetary systems. So now, here comes the most difficult part of this talk, that is explaining nulling interferometry. So I will take my time and try to explain in a different steps how the technique is working. And I will start by talking about diffraction. That is something that is limiting us a lot when we are observing targets in astronomy. So if you take a telescope, if you buy a telescope in a shop that is a diameter d, and you observe a star that has at a certain wavelength, what you will get is not an image of this star with its diameter. You will get this kind of blob here, which like that we call an airy disk, that is limited, so its size is limited by the wavelength and the diameter of your telescope. So what is interesting is when you try to observe a second star or a second object that is close to this star, then the problem is these airy disks, if they are too close together, so if the two stars are too close together, you will not be able to distinguish between the two airy disks. So you will be in the case where the two stars are not resolved. And the limit where you are able to resolve these targets is lambda over d. I hope you can read it. It's a bit white on white. Lambda over d, so it means that your angular resolution limit, where you can distinguish two objects, is limited by your telescope and the wavelength of the light you're using. So if you want to resolve like companions, planetary systems that are close to a star, you need to go to lower wavelength, and also you need to increase the diameter of your telescope. So one famous example is the extremely large telescope that is being built at Paranal at the moment. So the diameter will be 39 meters. And with this angular resolution, it will be able to resolve a house, let's say, on the moon. So this is interesting, but the problem is it's technically difficult to increase the diameter more than that. If we want to reach the inner region of a star, if we want to increase again the resolving power, we need to go to larger diameter, and this costs a lot of money. So the alternative that we have is to use the technique of interferometry. In interferometry, the technique is using several telescopes. So instead of using one big telescope, we take two telescopes that are separated by B, the baseline B, and you observe both telescopes are observing the same star again. And when you combine the light collected by the telescope, what you will get is this kind of pattern. So you can still recognize the airy disk with like the same size that depends on the diameter of your telescope, but this pattern will be convolved by fringes. And the fringes will have a separation that depends on the baseline of the telescope, so the separation of the telescope. And this is very interesting because, again, if we want to observe another target, another star that would be located near the first one, then the limit for resolving this binary is not limited by the diameter of the telescope, but is now limited by the baseline of the two telescopes, which means that now, if you want to resolve closer targets, you need to increase this distance, which is technically easier than increasing the diameter of a telescope. Yes, so if you want to increase resolving power, you need to increase the baseline or, again, go to lower wavelengths. So we have a famous example that is the Very Large Telescope Interferometer, also located at Paranal in Chile. And here, so you have on the picture on top, you have a picture of the VLTI with its 4 unit telescopes, the big ones, with a diameter of 8 meters. And you have the 4 auxiliary telescopes, the ATs, that are a bit smaller. They are 1.8 meter diameter, but they can move around at different selected positions. And these ATs, the maximum separation that can get is up to 200 meters. So it will give us the same angular resolution as one telescope that would have 200 meters diameter. But of course, it would be for less, for much, much cheaper. And with 200 meters, we can resolve, let's say, a human on the moon, which is a huge scale of angular resolution. And now we go to nulling interferometry. So yeah, this is what I was planning to explain to you. Nulling interferometry is a specific mode of interferometry that was imagined by Ronald Bracewell in the 1970s. So the technique is, again, using several telescopes separated by baseline B and doing interferometry with it. But instead, in this case, you will apply a phase shift to the light of one of the telescope, so that when the light is recombined, when it was supposed to do a constructive interference, it will instead do a destructive interference and the opposite. So you have the same kind of fringe pattern when you combine the light, but the central one will be a destructive interference, and the light from the star will not be transmitted to the detector, which is very important because up to now I was showing you binary systems of two stars with the same magnitude, but when we talk about planets, planets are much fainter than stars. They are like millions to billion times fainter than their central star. So the problem is, if you're using classical interferometry, you can be limited to the amount of light from the central star, and you can be like photon noise limited when you try to observe the planet. So here you have an example where you have like the fringes of the star, and you have the fringes from like a fainter planets. And what is interesting is that if we zoom in on the central fringe here, there is a point where the light from the star is almost completely cancelled. It's not propagating to the detector. And at some point, the light from the planet is becoming dominant compared to the light from the star. And this position is what we call the null position. And this is the position we want to stay in when we try to image exoplanets with the most stability as possible. Okay, so there have been many nullers in the past. The first one was done at the multiple mirror telescopes in 1998. Then there was the Keck nuller in 2004, the Palomar fiber nuller in 2008, the Large Binocular Telescope in 2014, and GLINT in 2016. GLINT is the most recent one, but it's not yet open to the community. And the other ones have been like decommissioned. So the only one that is currently operational is the LBTI that is operational and open to the community. You can see me next to one of the telescopes to give you an idea of like the scales of this mirror. So all these nullers have unfortunately not been able to image exoplanets. Their main science cases was observations of warm and hot dust. And in the case of GLINT, and maybe others before, but GLINT was also able to resolve close binaries. And in case of the LBTI, its main science case is to observe warm dust, so a dust that is located to the habitable zone, but I will give more details about this. And LBTI has been the most sensitive nuller for the observation of this kind of dust, which makes it a very interesting instrument to use for this science case. So now I will maybe drink a bit before. So this is the first part of my thesis that is about using the LBTI to observe the warm dust or the exozodiacal dust. So maybe first, what is exozodiacal dust or warm dust and hot dust? So I will give a bit of an introduction to this. Exozodiacal dust is a type of debris material. So debris material is any kind of material that is left from the formation process of the planetary system that didn't form a planet or a dwarf planet. So it's including the asteroids, the comets, the dust, all of these material that hasn't formed a planet. In the solar system, well, in the exozodiacal dust is also located in the inner region of the system, like around the habitable zone. You can see an example here. This is the zodiacal cloud in the solar system. That is the dust located around the habitable zone where the orbit of the Earth is. And you can see the dust that you can observe at the sunset or the sunrise. If you have a nice clear sky, you can see the scattering of the solar light before the sun goes up the horizon. And of course, it's been detected around other stars in the universe. It's been detected around 20% of other main sequence stars. It's mainly composed with silicates and carbons. And for the solar system, it's been especially thought that it was originating from comets. So I will make a sketch to try to explain how like this exozodiacal dust and the formation process. So here you have a typical example for a sun-like star with the different distance and the black body temperature that you get according to this distance from the solar irradiation. So exozodiacal dust is located here in the inner region of the system, and you have two types of exozodiacal dust. You have the hot dust located quite close to the star, like almost inner to the orbit of Mercury, while the warm dust is located more in the habitable zone. And you have another important type of debris material. It's not exozodiacal dust, but it's a debris material that is very important for what I'm about to explain to you. It's the cold dust, or the outer dust, or the outer belt, or exo-Kuiper belt. It has many names, but it's basically material that is located further out in the system, way beyond the snow line. And why is it important? Because we think that this is where this exozodiacal dust can be originating from. So some papers are advocating for exozodiacal dust to originate from comets, so comets coming from the outer region of the system. And when they arrive close to the sun or the star, they start to evaporate and release material in the inner region of the system, creating this cloud of zodiacal dust. So you have some papers advocating for this phenomenon in the solar system, but also outside of the solar system. And you have a second type of phenomena that is called the Poynting-Robertson drag. That is typically when you don't have a giant planet that is around the snow line, like in the middle of the system, that it would be scattering the material. When you don't have this type of giant planet, we expect that the cold dust located outer in the system will naturally drift, slowly drift inside the system. And as the dust particles are getting closer to the star, they will start to warm up and become warm dust. So these two systems kind of like coexist together. And they've been studied by different surveys and different observations. So for example, the LBTI was especially used to observe warm dust and compare it to previous observations of Spitzer and Herschel in the far infrared to try to see for the cold dust. And they have found a correlation between the presence of the cold dust in the outer system and the presence of the warm, the exozodiacal dust inner in the system. So there is a likely source. It's likely that the source of this warm dust is then coming from this outer belt. But then other studies, like especially near-infrared interferometric observations, have been done between the hot dust and the warm dust, but no correlation was found between these two, which means that the origin of the hot dust and its connection to the warm dust and the outer disk is still very much unknown and a topic of research. So now I want to talk about my work in this thesis that was about the special case of Thidebou. That was an interesting target because Thidebou, so it's a solar type star that is located in the Bootes constellation. It's an F-type star that is 14.5 parsecs away, so quite close to the sun. It's about the same age as the sun, between 3 and 5 billion years old. And it's been observed by the LBTI in 2017, 2018, and 2023 as part of the HOST survey. And what was found around Thidebou is that it looks a bit like this. There is a lot of warm dust, a huge signature of warm dust located around the habitable zone of Thidebou, but no sign of cold dust from Spitzer and Herschel. So no sign of like a massive outer belt that would feed this warm dust. So there have been some question about like, what is the origin of this warm dust? Where is it coming from if it's not from an outer belt? This is like breaking the correlation that was found by the LBTI. So that's a question. So the study was about trying to find what is the shape of this disk. If we find the shape of this disk, can we relate it to an origin? Can we find where the dust is coming from? And also about what is the composition of this dust? Can we use this composition to try to find where this dust is coming from? So here are some key results that were found. So the disk of dust of Thidebou has been constrained. There were three main geometry that were used to try to constrain, but it was not. We were not able to constrain which geometry was most likely. So we used the three, and then we were finding the evolution over time over the different observation time in 2017, 2018, and 2023. And what we could find when we were trying to constrain this shape of the disk is that the amount of dust in the inner region of the system seemed to increase. You see that in every case, it looks like the dust is getting closer to the star, which is not possible because this would mean that the dust is going quite fast. So this cannot be explained by PR drag because this is going way too fast for this. So there's some sort of increase of dust in the inner region of the system that is not really explained at this point. And using these models, we were also able to constrain the size of the grains, which is likely between 3 and 5 micrometer. So the conclusion that we have is that we cannot confirm the origin of this dust, but we know that it's likely not from PR drag because the time scale of this evolution is too fast to be explained by PR drag. PR drag is something that takes like 10,000, like millions of years to process, and here it's way too fast. We see an increase of the amount of dust, or like the brightness of the dust in the habitable zone of the star, which is something that has never been found before. So it's still tentative, so it still needs to be confirmed by new observations, but it would be the first time that we see this phenomena, and that is quite unexplained. So overall, the conclusion is that we need new nulling observations and new improved nulling observations to try to solve this special cookie that is theta-boo and try to find what's going on in this system. And talking about new nulling observations, I want to move to the second part of my thesis that was about the Asgard NOTT instrument for the VLTI that is nulling used to observe exoplanets. So I told you about the history of the nullers. The last one that was installed GLINT was in 2016, so that's some time ago. And now we're working on a new nulling instrument for the VLTI in Chile that is NOTT, that should be installed at the VLTI in 2026, so next year. So this is coming very soon. So the NOTT instrument is part of the Asgard visitor instrument for the VLTI. It's composed of 4 instruments. You have Boulder, that is the wavefront sensor that is correcting the wavefront aberrations that are originating from the atmosphere, for example. You have Heimdall, that is the fringe tracker. A fringe tracker is one of the most important parts of an interferometer because this is what keeps us to the null position that I told you about a bit earlier. So this is very important in this case. And you have 2 science instruments that are Bifrost, that is a classical stellar interferometer that is working in the near infrared. And then you have NOTT, that is the first long baseline nuller in the southern hemisphere, and which will do like exoplanet imaging, but also exozodiacal dust, so the thing I was talking you about in the previous chapter. So the LBTI, I told you, was focusing on the warm dust here. NOTT will be able to focus on giant exoplanets, so young giant exoplanets located a bit after like the habitable zone where you have some warm dust, so at what we call the snow line. And it will also study the hot and warm dust, and especially the intricate, like the possible connections between these 2 dust, because as I told you before, like we haven't seen a connection between these two type of debris. So there's something going on here that the NOTT instrument will be able to observe. So about the exoplanets, what is the capability of the NOTT instrument? Is it really capable to observe planets? So here you have quite a complicated graph, so I will spend some time to explain it. In the y-axis, you have the contrast of the simulated planets. So if you go below, these are like fainter planets. If you go on top, these are like brighter planets. The x-axis is the separation between the star and the planet. So on the left, you have planets that are simulated, that are quite close to the star. And as you move to the right, the separation is increasing. And then what my colleague did in the papers that you see here is that they simulated the population of planets around stars around the sun with 2 formation processes. In red are planets that are forming with core accretion mechanism, and in blue they are forming with gravitational instability mechanism. I don't want to go into the details of like the difference between these 2 formation processes, but overall, gravitational instability planets, you see, are much easier to detect because they are usually much brighter and further out in the system. While core accretion planets are usually fainter and closer to the system. They are like in red here. So in green, you see the VLT instrument in Chile and its detection capability. And you see that the VLT is not really able to probe core accretion planets, or not like the region where the core accretion planets are the most likely to be. But the NOTT instrument, when you see its detection limits, you see that it's able to probe this region where core accretion planets are very likely to be. And so when you calculate the exoplanet yield, so the amount of planets we expect to detect with NOTT, we find that using the Gaia proper motion observations, we expect to recover 5 core accretion planets in total and to do extensive studies of these core accretion planets, which is a very huge result, because if this is possible, this will be the first time that we can do an extensive studies of such planets, because with the current instrument, the core accretion planets are very difficult to detect. So this is about planets. So these are enthusiastic simulations. And then there is a second science case, that is the exozodiacal dust I was telling you about. So here you have on the x-axis the dust brightness, and then the number of detection in the y-axis. And you see that the LBTI, as I told you, was the most sensitive type of instrument for warm dust detection. And indeed, it's been able to observe fainter dust, like fainter disk, much fainter than what the other instruments were able to do before. So the NOTT instrument will be able to complement these observations also of quite faint targets, but in the southern hemisphere. This will be the first nuller in the southern hemisphere, so it will be the first one to use the technique to observe the warm dust of stars from the southern hemisphere. So we expect to be able to complete this graph and add new detection. And this will also be the first nuller to work in the L band, so with light between 3.5 and 4 microns, which will enable, as I told you, which enable to study the connection between the hot and warm dust. Okay, so enough about science. Now let's talk about instrumentation. So here you have the optomechanical design of the Asgard instrument as it will look like at the VLTI. So you see the 4 purple beams are coming from the VLTI lab, from the VLTI telescopes. So first you have the fringe tracker in purple. Then on the upper table you have the Balder instrument. In red you have Bifrost, and in dark you have the NOTT instrument. So I made a small animation to show you the propagation of the beams inside the design. So let's start. So you see the 4 beams are starting here. Then, doesn't work. Yes, then they propagate in the Hemdahl instrument first. They are going first through the deformable mirrors when they are correcting for the wavefront aberration from the atmosphere and also from the vibrations from the instrument. And then they are going through the NOTT instrument, going inside the delay lines, and then the 4 beams are recombined into one and then sent to the cryostat. This is one of the most important part of the optical design of the warm optics. It's the slicer. It's an optical system with 4 slices of mirror that are taking the beam arriving with different angle and then reflecting them to the same direction to recombine them inside the cryostat. So then the beams then going to the cryostat. Here's an upper view of the system with a few important optical parts. So this is all summarized in my 2024 paper. One of the important and new type of system we have that is designed by Romain are the LDCs, the longitudinal dispersion compensators. They are a kind of new system that is here to correct for the chromatic phase difference coming from the water vapor and the CO2 in the atmosphere. So water vapor has been corrected, like we have systems already from the Keck nuller to correct for water vapor, but CO2 is the first system that is here to correct for the chromatic phase difference coming from CO2. Then you have the delay lines. The delay lines are here to change the optical path distance that is traveled by each beam to equalize it with maximum balance, which is very important for when you perform interferometry. You want each beam to travel as much as possible the same optical path difference. Then the beams are going to the tip tilt mirrors for the alignment, the slicer, and then just before the cryostat, they are going through the monitoring system. It's just a system with cameras that are here to help us align the beams before they enter the cryostat. Inside the cryostat is one of the most important optics of the system, that is the photonic chip. It's made of gallium lanthanum sulfide, the GLS glass, and it was made at the Macquarie University. So this chip is used to generate the nulling interferometry for our system in a passive way. So I will explain a bit later. It was tested at the University of Cologne. And then, so to generate interferometry. And then as we finish generating interferometry, we feed the light to a spectrograph here to get the spectrum of the planet that we want to detect. Okay, so going in a bit more details about how the photonic chip works. So this is a kind of zoom in of a sketch of how the system works. So basically the 4 telescopes are observing a star-planet system, and then we inject the light of each of the 4 telescopes into 4 entrances that are quite small. They are 20 micrometer diameters, so you need to be quite precise when you inject them. And then the light of this telescope is being coupled into a system so to generate the interference. So when you generate the interference, after this, the light from the star is going to the outputs 2 and 5, while the light from the planet is going on the second coupler, where the light is again recombined and sent to the outputs 3 and 4. That are the outputs where we expect to find the light from the planet. So you can see that thanks to this coupler, this interferometric coupler, we're able to separate the light from the star and the light from the planet. And if you look at the 2 central outputs, this corresponds to the figure I was showing you at the beginning, this nulling position where the light from the star is ideally perfectly attenuated, while the light from the planet is transmitted. This corresponds to the 2 outputs here. And now the challenge is to stay at this null position with the highest stability possible. Because you see, if you deviate from this null position by just a bit, the light from the star will very quickly overwhelm the light from the planet. And as you go to fainter and fainter planets, you need more and more stability on this null position to avoid being overwhelmed by the photon noise from the star. So this is one of the main goals of nulling interferometry, is to be able to stay on this position. Okay, so now I want to talk about the test bench that we have in Leuven. So this was all the optical design that was done from in 2023, 2024, but we implemented this at the KU Leuven, and we got some results and some null measurements that I want to show you. So this is when the test bench was assembled. You can see on the left, this is where we got the new lab and the optical bench in April 2024. You can see me and Gert at the back. And I remember Gert was looking very happy about seeing the optical bench that was transported. And I was very, very stressed because I was seeing my PhD dangling in the air like this. And I was a bit nervous. But you see, everything was fine. And then after 1 year, the test bench was assembled. The optical design that we did was assembled correctly and operating correctly. So this is a sketch of how it looks like. It's quite similar to the optical design that you saw in the animation. There are only a couple of differences. The first one is that we don't have any telescopes in Leuven. Well, we did have one on the roof of the building, but I think it's gone now. So we don't have the 4 telescopes of the VLTI. So we need to generate the light beams in some way or another. So we use this system to generate the 4 beams and send them to the system. So this is what we call the VLTI beam simulator. We have a system of pair of mirrors that you see here, where we installed piezo actuators. So piezo actuator is an actuator where you when you give a voltage, you will deform the shape of the piezo, and then you can move a bit the mirrors, translate a bit the mirrors to change very slightly the optical path distance that each beam is traveling. So that's a very important system that we can use to adjust our position and stay at the null position. So to what we call the co-phasing of the beams. And then we have the rest of the system that looks very similar to what you saw in the animation, because it's the same optics that the one we will send at in Paranal in Chile. The only difference is you see the cryostat is not at the end of the bench. It's a bit aside because unfortunately the optical bench was a bit too small, so we had to refold a bit everything so that it would fit on the optical table. This is a picture of the inside of the cryostat. You can see the photonic chip I was telling you about. So the plan is to just inject the 4 beams on the right, inject the beams inside the chip, then the chip is doing the interferometry, the nulling interferometry, and then we'll recover the different outputs there to send it to the camera. So this is what we will see. This is what we see on the camera with the 8 outputs. And then if we play with the piezo actuator, you can see that we select each pair of beams individually. So here you have the beam 1 and 2 on the left. And then you can move the piezo to scan a bit the fringes and analyze each pair of the beam. And you can see that the light, by scanning with the piezo, you can redirect the light in one or the other output. And so what we do is that we do this scanning beforehand so that after this, we can construct a matrix from which we can recover what is the nulling position. So what is the position of the piezo that we can go to have the null position? Yes, and I think that's the last one, so the beam 3 and 4. Yes. So after you do the scanning and you get the position of the piezo that are needed, you can go to the null position. No, like this. So you go from a position where the light is going a bit everywhere without any direction, to the null position where you can see that all the light is going to the outputs where you have the little star, and the outputs that are meant for the exoplanet light have the minimum amount of light from the source, which makes sense. We shouldn't find anything in these outputs because we don't have any exoplanets in our source. Our source is basically simulating one star, so we should have the minimum amount of light in the central outputs. So then from this measurement, we can estimate the contrast. So what's the minimum minimum contrast that we can achieve with our instrument by doing the ratio between the light that we get in the 2 central outputs and the bright light that we get for the star. So by doing the ratio, we can get the contrast of our instrument. So you can see here a measurement we did over time of the different contrasts that we obtained. So what we get is that at cryogenic temperature, so this is important. This is the first time that we did the cryogenic measurement with this chip. What they did in Cologne is a warm measurement, like at ambient temperature. So this is the first time that we did a measurement at 140 Kelvin to make sure that the chip was working fine. And what we found is that we obtained a raw broadband contrast of about 1%, which means that about 1% of the light of the source is going in the central outputs instead of going to its bright outputs. And the goal to observe exoplanets is to reach 10⁻3, so an order of magnitude. So we still have some work to do to have the contrast that is needed before we send it to Chile, to the observatory in Chile. And another important parameter is the throughput, because we are observing planets. Exoplanets are faint targets, so we want to save as many photons as possible when you observe it, because otherwise you will start to be dominated by the background. So, and right now on the system, the element that is where we are losing the most photons is the chip. At the chip, right now, the test that people did in Cologne, they were finding a transmission of 37%, which means that only 37% of the photons that you're bringing to the chip are actually reaching the camera. So the goal is that we're able to reach 50% of transmission just for the chip. And overall, for the whole instrument, we want to achieve a 10% transmission. Okay, so I want to finish with a bit of status of how the Asgard instrument is going, because it is being installed and commissioned right now at the VLTI. Here are some pictures of the team that assembled it during this summer. So I wasn't there, unfortunately, so you don't have to look for me in the pictures. And this is the final version of the Asgard as it is. For now, it's only the fringe tracker. The Heimdall instrument is the only one that has been installed, but it's one of the most important ones. And they are doing the commissioning at the moment. So here's a picture that is only a few days old, where they managed to generate fringes with Heimdall with the different baselines of the 80s. I have to say, I don't really see the fringes in the picture, but I'm sure they're here. So the commissioning is going well, and they managed to generate fringes, so everything seems to be well to go and install the NOTT instrument. So some conclusion. The NOTT instrument will be the first nulling instrument in the Southern Hemisphere and at the VLTI. So it will complement the LBTI that is located in the Northern Hemisphere in the United States. So the NOTT instrument will be able, like the LBTI, to observe and study the prevalence and help us understand exozodiacal dust. And NOTT will also be the first nulling instrument to observe and image young and hot giant planets, which is what nulling interferometry was intended to do. When Ronald Bracewell imagined the technique in the 1970s, he thought about using the technique to observe exoplanets. And it's only now that maybe we'll be able to actually observe planets using this technique. And observing this planet, these young giant planets quite close to the system, will help us to understand the planetary formation that is happening in this system by finding if the planets are formed with core accretion and gravitational instability processes. And also for the future, this is very important because this will be a huge milestone for future nulling instruments that also want to observe exoplanets, and especially the LIFE space mission proposal that wants to focus on observing habitable, like planets located in a habitable zone of sun-like stars, not sun-like stars, like main sequence stars, sorry. And that will use the observations of NOTT and possibly the successful observation of exoplanets with NOTT as a motivation to make this space mission. Okay, and I am finished, so thank you very much.
No, wait, I'm not properly using it. Give me a second. I think battery is flat.
It was working just before. Maybe you can use this one.
Yeah, but for the jury members.
Yeah, it's true.
Anyway, then we'll figure out. Okay, so everyone hears me loud and clear? Okay, so thank you, Germain Garreau, for the perfect timing, the very nice introduction to the work you have done. So we will now go to the second part of this defense, which is the discussion. And so perhaps, oh, sorry, I am an experimentalist. So. Okay. So let me first, before introducing the members of the jury, for those of you who had no three defenses this week, a bit of a short explanation. So we already had, let's say, of course, after 4 years of hard work, there is already, this today is the public defense, which in essence means there is also a private defense with all the members of the jury, either in person or, let's say, online. So it's a very broad field of research. Therefore, there is a very large committee Germain then passed, of course, this first term. He upgraded his thesis, and that's why we're here today for the public defense. But still, it's science, so it's about asking questions and getting more knowledge. So therefore, today, I want to give the floor to all members of the jury for a final questioning. Moreover, at the end, there is also now ample opportunity for all of you to ask the question you always wanted to ask. Good, but before starting, let me introduce you all the members here today, either on-site or online. We have the supervisors of the work, which are Denis de Frère, Azura Bigioli. I'm not sure if she is here. No, but then we have Dr. Romain Laugier from the physics department, the Department of Physics and Astronomy, of course, with this audience. Then we have Professor Thierry Beverbist from the chemistry department. We have Dr. Gert Raskin here from the same section, IKS. Then as well here, joining us from Grenoble, France, we have Professor Jean-Philippe Berger sitting here at the front. And then we have three online presence of online jury members. Sorry, we have Professor Lucas Labadie from Köln, Germany. Then we have Dr. Steve Ertel from the University of Arizona, who is here. And then we have finally as well Dr. Claudia Palladini from Chile, from the European Southern Observatory in Chile. So that's it. It's a very broad jury. So ample questions will be given. So we have the tradition to start with the forest and with astronomy. There is huge distances to be traveled. So we will start. I will give the floor to Dr. Palladini. The floor is yours.
Thank you. Can you hear me? Can you hear me?
Yeah, sound is perfect.
Okay. Good. Well, first, congratulations, Germain, for this wonderful work. You showed us a bit into this presentation, but looking through your thesis, you really spanned through different fields, start touching very part of research from what you were calling like science, which is the observation, astrophysics part, and then you also went very much into instrumentation, and this was very impressive, and it was really a pleasure to read your work. I have a couple of questions for you. The first one is related to your Tau Botis work, where you mentioned the worm dust, the fact that you don't have any coal dust. Can you please explain to us what are the assumptions of your models and how they affect the results that you are presenting?
Thank you, Claudia. I think we can hear me. Yes, thank you. Yeah, indeed, the results that I've shown you are based on like a lot of assumptions that can be questions. So the first one, I would say, the first assumption is that the theta boost system is face-on. So this is quite a big assumption when you try to constrain the shape of the disk of dust, because if you have any inclination, this can change a lot the location of the dust. So this was based on like the stability of the null measurements that we did with the LBTI. And based on this, we assume that since it was quite stable with nulling interferometry, this means that it's probably a face-on system. So I would say like this is one of like the main assumption I would say of the work. Yeah.
And how did you decide to take this assumption? So so why did you decide to use this assumption? Were they based on other observations, other?
No, unfortunately, like only the no, sorry. Deactivated my microphone, sorry. No, unfortunately, the problem is it was only observed by the LBTI, so we don't have other observations to compare this assumption, which is like a problem. Like it would be nice to have other observations at different wavelengths to try to constrain a bit more the inclination. The main reason is that it was the model that we had could not use, like we couldn't let the inclination as a free parameter at the same time as the geometry of the disk. So we had to make some assumption on the geometry. And so the most likely was that the disk was face-on based on the LBTI observation. That was the most likely hypothesis. So this is what we decided to work with that. But obviously, we need other observation. We would need observation to try to constrain this inclination. But there's also, maybe I can talk about like the other assumption is that the disk is thin, is vertically thin. And that's another big assumption because we don't have any proof that actually this disk is not puffy and or like is not thick. And if the disk is thick, then the model doesn't apply anymore. So we would have to develop a completely new model to try to constrain the inclination, the thickness, the geometry, and this starts to be a system. So basically this work is based on a thin, vertically thin disk face on.
Okay. So are there plans to bring this work further? Or what kind, do you think that you should repeat observation with the LBTI or another instrument? I don't know.
Well, unfortunately, I don't think if there's another instrument that could observe, like there's the CHARA, but the CHARA observatory that would have the angular resolution, but I'm not sure if the instrument like in the K-band would be able, they've been able to observe like hot dust before, but it wouldn't be like the same region as in the N-band with the LBTI. So the plan for now is mainly to repeat observations with a better detector. So they are upgrading the detector of the LBTI. They have a new system, they have a new data reduction system to reduce the noise level from the observation. So thanks to this, hopefully we can make new improved observation with less noise, and then we can use that to try to constrain a bit more the shape of the disk.
Okay, thank you. Let's go to slide 65. Seems like your thesis is very much about reducing the noise, right?
Yes.
There's a lot of attention about this. You were mentioning here like how important it is to reach the null position and that you have a certain goal and you are not yet there. And you mentioned that there is still some extra work needed. So what is this extra work?
Yes, excellent question. So I'm happy you asked it. So the null measurements we did here was only with 2 beams. So we only had 2 beams and we canceled these 2 beams together. So we had like a raw null. But the reason we have like a 2-stage coupling system in the chip is that we want to do some kind of kernel null. So we want to use a double Bracewell null. So the double Bracewell null is basically taking 2 pairs of beams, doing the null, and then recombining the null again in a coupler. And this way, when you when you subtract the 2 nulling outputs, you can actually correct for some like slight phase difference that are coming from like some phase error coming from the atmosphere, and you can reach this 10⁻3. So this is actually the measurement that was done in Cologne. They had a measurement of the raw null that was around 1%, so what we had. And when they subtracted the 2 null outputs, they were able to reach a 10⁻3, or like very close to 10⁻3. So it's what we call like a differential null that gains like an order of magnitude on the row contrast. So this is the plan, but it's more difficult to co-phase 4 beams and to find the null position for 4 beams than with 2. So we only had the time to do with 2 beams in the thesis.
Okay, thanks a lot and congratulations again. That's all from my side.
Thank you, Claudia.
Okay, thank you, Claudia, for the questioning. And then we move to the USA. Dr. Steve Ertel, the floor is yours.
Thank you. Hey, Germain, that was a very nice presentation of obviously very important work. Very well done. So on the, I want to drill down a little bit on the theta bu inclination and disk, thin disk that you mentioned. So you make this 2 very important assumptions on your model, but can you comment on whether the data actually, constrain this, or whether there's any impact really on those assumptions on what your model would produce?
So you mean like on the assumption I made, if there is like any impact on the
So-
model that I'm doing?
Let me try to clarify. Say your disk would be edge on instead on face on.
Yes.
Would you actually see a difference in the data that you simulate compared to the data that LBTI has produced?
Yes, if the disk is vertically thin, which we have no way of knowing, actually. It's like a general supposition. If the disk is edge-on or has like a high inclination, then yeah, we would see from the transmission map and the rotation of the transmission map throughout the year, we would be able to see a clear difference in the null measurements that we have. So assuming our disk is a thin disk, then the face-on or like a low inclination is quite likely. But if the disk has thickness, then there is a degeneracy between the inclination of your disk and the thickness, and then it becomes very difficult to untangle the two parameters. And then in that case, we make an hypothesis, but we don't have a way now to check this hypothesis with the current observations.
But then your main conclusions of that work, I think, are that there's a tentative sign that the brightness is changing, and there is a sign that somehow the size of the system is getting smaller, or there's more dust coming in the inner region, right? So one of the two, I would say. Would that change at all? Those conclusions, would they change at all if you assumed an edge-on disk?
Yes, I would say so. If it was an edge-on disk, because like, how could we? I don't know how different it would be if it was an edge-on disk. Well, at least if it was having like a high inclination, I think we would see a difference. So at least like in the shape, we wouldn't be able to. If the disk is edge-on, it's more difficult, I think, to see the increase of brightness in the habitable zone specifically, because like since it's edge-on, if you have an increase of dust brightness close to the star, you don't really know if it's in the habitable zone or if a habitable zone, or if it's a bit before. So I think like if the disk is edge-on and thin, or like if it's if it's edge-on, then I think it's a bit difficult to try to constrain where the dust is in the system.
Okay. I have one other question really, and that's for the beam combination of NOTT. You're combining so the way you've presented this, you're combining all 4 telescopes into one really flux brightness measurement in the end, right? So how deep is your null? And this is great if you want to have a really deep null on a very simple scenery, like, a planet is a faint point next to the bright point. So, in this case, you want to have this measurement as precisely as possible. But
Yes.
in if you have something like a disk or dust distribution that's more complex, is there maybe a way to get more measurements more effectively and maybe at the cost of some of the precision?
So yeah, you mean that, let me rephrase to see if I understand correctly. So you mean like there's a transmission map, and there are some region of the transmission map where we're not sensitive to any emission, and you want to see like, is there a quick way? Because the option would be to wait for the rotation of the field of view until like these regions are in a bright fringe and we can detect them. So you're asking if there's a way to quickly scan the field of view and like this region where we have a low transmission?
Well, if I'm asking if there is a way to get maybe less degenerate and more less degenerate data that contain more information in a single observation than just one brightness measurement from 4 telescopes.
Well, in the way the NOTT instrument is designed, not really, because all the light from the field of view is like in a few pixels. So you are basically integrating all the light from the field of view in one. But if we would operate the NOTT instrument like the LBTI, we could like have a proper image of like the disk or like the exoplanet, like through the transmission map. And then we could use like the pixels and the apertures to locate it. For the NOTT instrument, I don't think there is a way, like the only way to recover this is like by doing long exposure time and like the change of transmission map to try to locate where the planet or like the emission is coming from.
Cool. Thank you. Those are my 2 questions.
Thank you, Steve.
Okay, thank you, Dr. Ertel. Then we move to Professor Labadie. The floor is yours.
Thank you. So I guess you can hear me, right, Germain?
Yes.
Okay.
Yes.
So I will also not be very long. I mean, I will take maybe just 1 minute to remind, how, in a way, challenging this whole thing was, I believe. So I would like really to congratulate you for putting all that together. I told you already, but I would like to repeat it here and have quite some sympathy in a way for, this kind of exercise where, you have to really be broad, and at the same time, you cannot be, superficial. So you really have to get into the detail of all that topic. So I think it's it's a difficult challenge, and I think to some extent, you solved it, very, very adequately. So I would like to congratulate you again. So that I would like just also to ask maybe a few questions. So the first one has to do, maybe you can show again your model again of the dust. And here I have that goes together with another question. So first of all, can you remind us in the situation where you're interested in the exoplanet? So how do you make, maybe that combines with what Steve was asking before, but how do you disentangle basically the signal of the planet essentially with a signal that is produced by the disk in that case? I think there are, of course, this is one of the fundamental hypothesis of Braswell, you rotate the interferometer. So in the case of NOTT, can you remind us how you do that?
Yes.
Your mic.
Yes, now it works. Yes, so we basically have 2 operational mode with NOTT. So we have so as I was telling Claudia, the main observable we have is the differential null. So we have 2 ways to obtain this differential null. We can subtract the 2 nulling outputs. This will give us an asymmetrical transmission map that will basically, if we have a face on disk like the one I have here, this will basically null the contribution from the dust, while asymmetrical source of light like exoplanets will be transmitted. So in this operation mode, we'll be sensitive to asymmetrical source and not centrosymmetric sources. But if we change the phase input and we add the 2 nulling outputs, then we will get sensitive to centrosymmetric emissions and not asymmetric emissions.
Okay, but going to that, I'm glad that you say this because I would like to go back to the first mode now, and that's why I wanted to see also that image. I mean, we see in those models that those objects are very centrosymmetric again, okay, because you cannot really, if understood correctly, you cannot really constrain basically the lack of symmetry. So, with very long baseline interferometry, you would ask yourself if there is a closure phase signature in that thing. But my question to you is, would you consider that most of those debris disk sources tend to have, I don't know, from the literature, from your experience, tend to have very little closure phase signal? Because if it's still asymmetric, you will modulate basically the disk signal the same way you modulate the planet. So what is the status of the knowledge on the closure phase, or let's say on the asymmetry or, so centrosymmetry of those, debris disks?
Well, I would say it depends on the presence of companions, of giant planets in the system that can maybe swap away the dust. So I would say that if you are in a system that doesn't have any giant planets, it's mainly unlikely, I would say, that you have big clumps or you have asymmetrical things in your substructures in your disk. But the problem is we are interested in giant planets, so we are tend to observe a system like Beta Pictoris or PDS-70, and in this case, we know giant planets tend to across their orbit, they tend to like destabilize a bit the system, especially in the early formation in the early phase of the formation process. We know that giant planets tend to destabilize a bit the dust. So then it's likely to create, I would say, substructures in the disk that we could see as maybe exoplanets. Like that can be a source of confusion in this case, because we might think like these substructures are planets. So that's indeed a risk.
And how do you mitigate this risk? I mean, at the end of the day, how are we going to know whether we have the modulated signal of a planet or the modulated signal of, not even talking about clump, but, you know, is it about the speed of modulation? Is it, how are you going to disentangle the two?
It's a good question. My assumption would be to repeat several observations. I'm not sure I see a way to do it in one observation, but if you do several observations, then you can calculate a bit the orbit of the object you're tracking and try to see if it's following the orbit of like a planet, like a Keplerian orbit, or if it's having like something a bit more funky type of orbit that would be like an indication that what we're observing is not a planet, but something else.
Okay. Okay. Well,
there's also observing like the spectrum. This it's also possible.
Okay. Okay. That's probably something that should make a difference. I have maybe again. I think we are supposed to be quick, so maybe I just have one additional question. Very simple actually. So I go directly to the your instrumentation work that we have been commenting already. What about the anti-reflection coating? I mean, do they work? No, it's a serious question. In the sense, I would like to know whether. So
I don't have any. Just coming back to the slide. Well, it's just like. Yes, I did a measurement. So we had like So I didn't try the coating on the chip, and the problem is we were not able to test the cryogenic measurements on the coating. So when it's still at the same status as I think the last time we talked. That at warm temperature we have a 50% improvement. Like when we do the coating on one face on the test chip, we have a 50% improvement on the Fresnel losses, but we still need to put the chip in the cryostat and then measure the transmission to try to see if the coating is surviving well.
Yeah, I think verifying that this thing does not delaminate, I think is probably the most important thing, even more than making the warm measurement, which probably will improve. But so you don't know yet at the moment, if I understand correctly, whether things delaminate or not.
No, we're planning to do new cryogenic measurements with the chip as soon as we can reach like the double Bracewell null position, and at the same time we want to put the test chip inside the cryostat and cool it down at the same time to try to see if the coating is resisting well.
Okay. Very good. So let's hope that it survives. And okay, I think, as I said, we're supposed to be quick, so I'm done. Thank you very much again, and congrats for the whole work.
Thank you, Luca.
Okay, thank you, Professor Labadie, for the questioning. Then we move here on site to Professor Jean-Philippe Bergier. The floor is yours.
Hello, Germain. I believe I was the first to meet you way before your thesis, because you were at the time looking for an engineering project. And most of the engineers of your school, usually they want to make money or contribute to a big, complex thing, and you were already very obsessed by doing research. And I think today that you've proved that you've been able to carry an ambitious project. And as Lucas said, it was a very difficult task. We've tried ourselves, and you've been much further than that. Of course, you are in a very good team, but it takes some guts to tackle this kind of difficult instrumentation project. And the last thing I admire in your work is that usually when you do a lot of instrumentation, it's very hard to turn to astrophysics because you don't feel confident enough, and you did that. I mean, you were very advanced in your PhD, and at some point you decided that you wanted to learn and to do an actual astrophysical project that led to a publication. And this is rare, and I congratulate you for that. So I'm really very impressed by your trajectory in research, and hope for the best. But I still have questions. So one of the motivation for having LBTI, I believe, was also not only to characterize exozodiacal dust, but also to reach the limits where we could identify targets for Earth for an Earth finding mission like life. It seems that we are not yet at the sensitivity requested to measure one Zodi. Do you have an idea of whether this can be achieved, this kind of sensitivity can be achieved from the ground? Or from your experience, what are the limitations in terms of sensitivity?
For the LBTI or...
For the LBTI, yeah, ground-based characterization of thermal...
In the N-band.
In the N-band, yes.
Yes. That's a good question, because for the LBTI, I'm not sure yet if we're limited by... I'm sure, yes, so... Yes, sorry. So definitely it's limited by the background of the atmosphere, and that's like the main source of noise. So about like, can we achieve a better sensitivity? I mean, with a better camera, we'll have to see like if it's improving the sensitivity, if there's a reduced detector noise. But then the photo noise from the background, there's not really any way to cancel it, right? So I'm not sure if the LBTI as it is can go lower in terms of sensitivity. At least from all the discussion I had with Steve and the papers I read, I'm not sure I remember like any argument to say that we can hope for a better sensitivity with this.
Okay. On the same type of domain, it seems that the instrument NOMIC can also work not in nulling mode, but in classical interferometry mode. Is there a way that you could use that mode to characterize a little bit better the system you're observing? So either by measuring the zodiacal dust directly or looking for a companion?
So yes, I don't have the details of how the FISO mode is working for the exozodiacal dust. I guess there's a reason for using the nulling mode instead of the FISO mode in this case. I guess it's difficult. So like the FISO mode, I know they want to use the LBTI to observe for like Earth-like exoplanets because they have the angular resolution for that. And they plan to use the FISO mode and do like a lot of short integration. Mm-hmm. So I think this is something that is possible, but it needs a lot of integration time. You need like a lot of short integration and then combine all of them to, at the end, maybe have something. And maybe it's not as efficient to do a survey. Maybe it's good. Maybe it would be a possibility for Thidaboo. I don't know.
Okay. Switching to NOTT now. So NOTT has a peculiarity. It's operating at 3 microns, and it has a continuously varying transmission map. So it adds a complexity because at these wavelengths, you might have a contribution from the warm and hot dust.
Yes.
And at the same time, you have a transmission function that is continuously varying. How do you think you should take into account that in your modeling? How will it affect the modeling?
So I think this is what Romain's been working on, like the NIFIT tool that is able to give you the transmission map, like during your observation, depending on like the orientation of the baseline, it can give you the transmission map. So I guess at the end, like you can use this transmission map for like try to deconvolve this and try to recover what is the actual, how does the actual source of light looks like. But it needs, yeah, it's true, it needs some work. It's not automatically done, but and it needs long exposure because you want the rotation of the field of view to cover a bit everything.
Okay, thanks. And last question. So you did decide, I mean, not you probably, but you had to decide to go for a design, optical design that used an integrated optics, which gave an extra complexity. Do you regret that? First, and then what would have been the challenges of going to a more classical bulk optics design?
So it was chosen at the beginning because it was thought to be easier. And I remember, Denis, that you said at some point that you thought that it would be easier and that you regretted a bit this decision at some point of using a photonic chip instead of the like beam splitters, the same way they use at the LBTI. I mean, definitely in terms of transmission, I think the chip is like we're losing a lot of photons with the chip. But I think in terms of complexity, we're still gaining because like recombining 4 beams with beam splitter would have asked like a lot more optics. And the problem is the more optics you add, the more you will lose photons and the more you will be background limited. So you want to reduce the amount of optics as much as possible in your system. And I think a photonic chip, although you're losing photons, but I think at the end, maybe you're gaining some signal to noise ratio compared to having a very complex optical system. Especially since in our case, we cannot put all the mirrors in the cryostat like gravity. So all the mirrors are at warm temperatures. So yeah.
Thank you and congratulations again.
Thank you, Jean-Philippe.
Okay, thank you, Professor Berger. Then we move to the KU Leuven, to the chemistry department. Professor Verbiest, the floor is yours.
Yeah, thank you. First of all, congratulations with this work. I really enjoyed reading it as a non-specialist and also liked your presentation a lot. Yeah, here, the slide is here. Your goal of contrast is 10 minus 3. You already mentioned that you can achieve that by that double nulling procedure.
Yeah.
What other improvements could you add to the system to even make the contrast even better?
Better than 10 minus 3.
Yeah.
Because we're in the lab, so because definitely on Sky you need to correct for vibrations. So this will be one of the main limitations that we have. So definitely this is something to work on. In the lab, I have to admit, I'm not sure what is limiting us in the lab at the moment. Why are we getting below 10 minus 3? I would say, how could we improve this? Maybe, well, one way is, for example, to reduce the wave band. So right now we have a filter from 3.5 to 4 microns. One easy way, like to get a deeper null, is to go to smaller bandwidth, but then you get less information. Yes. You can also use another system. I know that, yeah, for example, in Zurich, they managed to get null depth of like 10 minus 7. Although they are not in the same wavelength as us. I think they are in longer wavelengths, which is easier to achieve deep null. But they are using a different mechanism. Instead of a photonic chip, they use the difference of polarization. So they rotate the polarization for one of the beam, and then they combine it, and then this gives you an achromatic null, which we also get in the photonic chip, but it's not a perfectly achromatic. It's something that can be done. So that would be a solution, yeah.
What about the beam quality, for example? If you would be able to increase the quality of your input beams, would that be an option?
What do you mean by quality? Well, you mean like the strail ratio of the beam?
The shape of the beam. If we do an interferometry experiment in the lab, we want the Gaussian beam from our laser. Would that be an option?
So in our case, the shape of the beam is not a problem, because as soon as it's injected inside the chip, the light that is injected is exciting the Gaussian mode. So technically the beam should be Gaussian. So the only thing we can gain from working on the beam shape in the throughput, we can make the beam shape a certain shape that is more efficient to injecting the light in the chip.
Okay. And then just one final question, just out of curiosity. So you built that test bench, right, in the lab?
Yes.
You're going to move that to the VLTI?
Not me.
Okay, someone else.
Not just me.
But is that what you are actually going to use? Is it that equipment, those optics?
Yes. Yeah. Up to the photonic chip, well, we just have the lens, the injection lens to replace. The cryostat will be a new cryostat with a spectrograph. Right now, we don't have a spectrograph, so we can't spectrally disperse the outputs.
And then how stable is that system? If I build an optical setup and I go on a vacation for a week and I come back, I can guarantee you that it doesn't work anymore. So I was wondering how stable it is.
So in our case, I don't know how it will be at the VLTI, but I know that here we can go on the weekend and we come back and the injection is the same. The injection is not moving. The fringes are the same. We haven't moved so much, so we're still like way in the coherence of the interferometry. So stability looks pretty good, I would say, in the system.
Okay, good. Thank you.
Okay, thank you, Professor Verbiest. Then let's move again to our department. Dr. Rasquin, the floor is yours.
Okay, thank you. Well, thank you, Germain. Nice presentation, and also, well, congratulations on the impressive work that you have achieved over the past few years. To admit that I'm really impressed with what, the quantity and the breadth of the work that you've been doing. It's was an impressive work. So, just well, maybe first a remark, not a question. Somewhere half your talk, you said, okay, let's skip instrumentation and skip science and switch to instrumentation. I think it's not. Well, we should maybe step away from considering instrumentation as not being science. So I'm sure that what you've been doing in the instrumentation part was also done in a scientific way, and certainly
It's
building and designing an instrument is
science.
also part of science. Yes. Well, maybe just a question out of interest. So NOTT will be operating in the L band.
Yes.
The technologies that you now develop for NOTT, how easy would it be to extend, or how useful would it be to extend this to longer or shorter wavelengths?
The main limitation is coming from the chip. So the L prime band region was mainly motivated by the transmission of the chip and how achromatic it is. It's important that the splitting and the behavior of the chip is as achromatic as possible. And as you move to shorter or longer wavelengths, so longer, we can't really do that because as soon as you leave 4 microns, you have the CO2 dispersion kicking in the atmosphere, and then you can't really make fringes with that.
Yep.
But like for shorter wavelength, well, the plan was to first operate not between 3 and 4 microns, but the problem is the chip was just not achromatic enough in the 3 and 3.5 regions. So that's what's limiting the waveband.
But more in general, you can have chips in different materials, which are...
It's true, but then it's adding complexity to your instrument because I guess you need to split the light with dichroics, and then you need to send like this wavelength into this chip, another one to this chip. I have an injection, like an alignment and injection system for each of the chip. So for longer, like having longer wavelengths is, I think, quickly becoming a difficult, like complex instrument. And in this case, as a visitor instrument, this wasn't really the plan. Right?
But then more in general, and it was already partially answered maybe in making the choice for going to the photonic chip or not, but I'm not saying that modifying not for doing both, well, a broader wavelength range, but if you have to design an instrument for the shorter wavelength range, would you also go this route of building a NOTT version for shorter wavelength range, or would you do this differently then?
Well, I guess I would, because I was trying to motivate the Max Planck people to make a nulling mode for the gravity, so in the K band. The problem is, as you go to shorter wavelength, the contrast becomes quickly less because of the vibrations. So the science will be different. The science cases would be different. So I'm not sure if right now there would be a huge gain, well, from the current instrument. But then there is also, I think it would be interesting to do a nulling instrument in the K band and like shorter if you can, because like for exoplanets, it might not, you might not be good enough, but for dust, this would be good enough.
Yeah. And then maybe also something on throughput. You mentioned during your talk that there will be a total throughput of 10%.
Yeah.
So is this also including telescope, spectrograph, detector, or the whole chain, or is this?
No, it's the 10% is just the NOTT instrument.
Yeah.
The optical train of the VLTI and the atmosphere. The atmosphere, I think we were planning for a throughput of 30%, and the optical train, if I remember, it was 80%. So at the end, will be more like, I think, 3% of throughput with the atmosphere and the telescopes.
I completely understand that is major attention to null depth and the contrast and all this, which is perfectly normal. It always feels a bit painful that we lose so many photons on the way. do you see like future avenues or in maybe other technologies or whatever to really pump up this number of 10% or 3% of whatever to really, well, make substantial gains there, much more than just having a better reflection coating or so, but really to increase this by a relevant fraction?
With the photonic chip, well, I think it's what we discussed at the preliminary defense, like trying to change the shape of the PSF with a deformable mirror to try to increase the coupling efficiency from 80% to like 95%. There would be a lot of gains. Then maybe exploring new material to try to improve the transmission. But otherwise, with a photonic chip, I think it's difficult. It might be difficult to reach higher throughput. I think if you want to reach very high throughput, you have to go like for different architecture, like not photonic chip, but like with mirrors and like the polarization difference. But then you have some background limitations. So this is all a trade-off.
And then maybe one last question. Well, you already briefly mentioned Jake's thesis of last week, but he was doing very similar work in some way, a lot of instrumentation, also focus on exoplanets. So I thought let me just ask the same question as I also asked Jake last week. Well, you've both been doing a very broad kind of work. So what was the most surprising thing you came across during this complete PhD journey of designing and building this instrument, this part of the instrument?
That the instrument was working. No, it's what I was telling people every time. There's always something surprising to see the fringes. You always expect that for some reason they would be gone because of instability and something, but no, they're always here, always at the same place, always at the same position. So this is what happily surprised me about the instrument. There was no reason to believe that it would be otherwise, but it's always impressive to see it.
Okay, well, thank you. Congratulations, very nice.
Thank you.
Happy. It was a happy surprise.
Okay, thank you, Dr. Raskin. So in the public defense, also the PhD supervisors have the right to ask questions. So I have the pleasure to give the floor to Dr. Loger.
Hi, Germain. So thank you for this good presentation. I want to say again that I'm really impressed by all the work that you accomplished, and you've shown here only like only the surface of all the work that you accomplished. And yeah, I think especially in the part that we do, instrument science, there is a lot of unexpected things, and a lot of our work is dealing with the things that are more complicated than expected. So I was wondering if you would have something that comes up that was actually a good surprise. I mean, going maybe in a little bit more detail than what you just said, like that we actually could find the fringes, but something that worked easier than expected. Because yeah, we do spend a lot of time in the things that are more complicated. But yeah, do you have a more particular example of something that you feared, that you expected to be complicated, but actually ended up being simple?
I think the alignment with the slicer is something that we were quite afraid of when we thought about the alignment of the system. And the first alignment was surprisingly quick. Well, quick, like as it can be for first alignment, but it was surprisingly okay for the first alignment and for the system. This is something that we were all quite worried about it, especially at the VLTI. It's still something that we're quite worried of, but I am feeling a lot more confident about this now.
Okay, thank you. I hope it works again the next time we have to align it. Thank you.
Okay, thank you. Then to Professor De Frère, the floor is yours.
Germain, just a quick question from me. If you had to start over, what would you change in the design of the instrument?
I would put the chip vertical.
Why?
Because it would have made the slicer easier. I think it would have made a lot of things easier to put the chip. Well, this is what Romain was advocating, and we were very afraid of with Azzurra because we thought like the chip, vertical chip, is there like some kind of effect on gravity on the photons that would change something or deformation? But I think it would have made. I don't remember well. It was some time ago that we discussed about the design of the slicer, but I remember that it was easier if we had to put the chip vertical.
Okay, thank you.
Okay, thank you, Professor De Frère. Just to confirm, so Dr. Bighioli is not here. Eh? She's not present. Okay, okay, no, but just to I'm not missing her questions. Then, as stated, the final questioning can come from the audience. So if anyone has a question, I'm very willing to bring the microphone.
Hi, well done. I really liked your presentation. My question is about throughput. You said that the injection into the chip is 20 microns, I think it was, which doesn't give you much wiggle room for each of the inputs into the chip. Is that right?
The diameter.
Yeah, the diameter.
Yeah, the diameter is 20 microns, yes.
So are there micro lens arrays glued onto the chip or anything like that? And also they are? Okay, great. And
No, they are not.
Oh, they're
but
not.
It would be nice. We
Okay.
thought about it, but this is way more expensive.
Right. Okay. Yes. Also, do you have the ability? So I know that you have automatic piston tracking. Well, not tracking, but you can find the nulls through pistoning. Do you have the ability to tip tilt the beam injection at all?
Yes.
Yes.
So we have. I flew over the design, so I didn't spend a lot of time on this. But yes, we have 2 tip tilt mirrors for each of the beam that is here to optimize the injection in the chip and optimize the alignment of the system in general.
Cool. So I was wondering if you could use that for amplitude tracking because
yes.
So is that in
so
the
this is
works
the
as well?
plan we have right now is to indeed any amplitude imbalance and any intensity imbalance between the beams. We plan to adjust that by slightly de-aligning the beams that are too bright compared to the other ones.
So one really quick question. I'm sorry. What would be your, I guess, sensor for detecting, like how you have wavefront sensors? What would be your sensor for detecting whether, in which direction you need to tilt your beam to match the amplitudes?
The direction for like the movement of the beam,
Yeah,
or the
you have
direction in
a
terms
2D
of which beam should we disalign?
Which direction for the beam? Because tilting it one way can do the same thing as tilting the other way. You need to know in which way to tilt the beam.
Well, there might be a difference on the direction, but since we're getting the photometric output, so we're getting a feedback of how much light we inject and what's the actual imbalance. So what we can do is that we can just move it in one direction and we stop at the moment where we have the right intensity.
I understand. Cool. Thank you.
Thank you.
Okay, thank you. Anyone else? I asked for questions, so okay.
Hello, Germain. It was a pleasure to see your defense today. Thank you very much for that. I highly appreciated the fact it was very understandable in spite of the fact I'm absolutely not an astrophysicist. My question would be, among all the stuff you did in your PhD, what is the thing for which you're the most proud of?
I think this. No, it's no. Aside from the joke, it's because like a null measurement is like the very typical thing that any nulling instrument needs to perform. And you have to understand, when I started my PhD, there was nothing. When I started the first day, Azzurra led me to the lab and there was the black body source and that was it. And I was really not sure if at the end of this PhD, I would manage to get a null measurement. That is like, it's It's something that you show to a bit everyone in the nulling community, because this is a bit of a proof that your instrument is working. So it's been a bit of a rush to get this at the end of the PhD, but I was definitely proud, especially at cryogenic temperature, because I spent a lot of time on the cryostat. So I was definitely proud to see that we get a null measurement with excellent stability, very, very good stability in the lab.
Congratulations.
Thank you.
Okay, then perhaps the final question. No.
Hello, Germain. Thank you again for the presentation. I agree with Natalie that it was very understandable, and I really appreciated that. The slide is perfect. My question is about the temperature, because you mentioned the fact that at room temperature, you had the same low broadband contrast than at cryogenic temperature. So in the general way, I know why we go to cryogenic temperature, especially when we are in the infrared. So why did you go to this temperature here with the same at the end low broadband contrast?
Yes, because at the end, the instrument will, like the chip, will work at cryogenic temperatures. Even lower than this will be at 90 Kelvin. So the plan is to check that it's working well. And it's working the same way at ambient temperature than it's working at cryogenic temperature. So the plan was to check that there was no, like when the chip is contracting at cryogenic temperature, we had to check that there was not any problem in the manufacturing or anything that would completely hamper this null measurement.
Yeah, but why do you need to go to this temperature if you have the same result as in the room temperature?
Oh, then because the reason is that in the lab we don't have a lot of background. Well, we have background from the environment, but this is nothing compared to what we have at the observatory, because we have a lot of background emission from the atmosphere. So this is what we need to limit by cooling down the chip, adding a cold stop to crop this emission from the background and all the VLTI lab. So that's the main reason.
Okay, and just to finish about the temperature, what do you think about putting all the lenses and mirrors at cryogenic temperature? What would be the result and the gain in the low broadband contrast, do you think?
I would not be able to quantify it. I just know that this would be a gain in stability, because then you have a much better control of the temperature and pressure and humidity in your system. So it's expected to be much more stable during the night. Here, it's cheaper to work at ambient temperature for most of the optics, but then it means that during the night you need to occasionally realign your system, because there are drift in temperatures and pressure inside the lab, so you have slight misalignment. So you need to now and then realign your system. So you lose some time, but you lose some money too. Oh, you gain some money, sorry.
Thank you and congratulations.
Okay, thank you. Then I think I will stop this part of the session here. The jury will go for the deliberation. Wait, we will come back in 10 or 15 minutes. Yes. Okay. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for granting the doctoral degree in science, astronomy and astrophysics. I think it's working, no? Oh, sorry. Okay. Yeah. Good that you... okay, sorry. Germain Garreau has presented to the faculty the PhD thesis on the topic nulling interferometry from exozodiacal dust with the LBTI to explore exoplanets with Asgard NOTT at the VLTI. In partial fulfillment of the requirements for the PhD in science, astronomy and astrophysics. And Germain Garreau has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of the KU Leuven, I confer upon Germain Garreau the degree of Doctor in Science, Astronomy and Astrophysics. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described by the ALEA European Code of Conduct. Reliability, honesty, respect, and accountability. I close the session. Germain? Congratulations. The chairman of your defense. You have to sign this, then it's official. This is also for me, and I give you the no problem, and the dates, then we all agree that we got it. This is for me. Super. Okay, so please take a seat. Then there is laudatio by the supervisors of Germain, and my job is done.
Okay, does it work here? Okay, yeah. Okay, thank you very much, Joris. Dr. Garreau, congratulations. That was a really amazing job and presentation. Let me start by saying a few words in French. Félicitations, Dr. Garreau. C'était vraiment un plaisir de t'avoir parmi nous pendant ces 4 ans. Je veux te remercier aussi pour tout le travail que tu as fait. Tu as fait un énorme travail, on l'a vu tous aujourd'hui. Tu as couvert l'instrumentation, la science, l'outreach. C'était vraiment agréable de t'avoir dans l'équipe. Nos échanges le matin à la cuisine, où on parlait des problèmes du jour, c'était chouette. Je voulais remercier aussi ta famille d'être là et pour le soutien qu'ils t'ont apporté pendant ces 4 ans. Finir une thèse, ce n'est pas toujours facile et j'imagine qu'ils ont contribué à ce succès, qui est très important, évidemment, pour l'équipe ici. Now I will continue in English. So congratulations again. It was great to have you. And I know it was not an easy PhD, right? It was, as you said before, and it was said by Luca, when you arrived, we had nothing. We had no lab. We had one black body source, right? And so you had to do everything mostly yourself, the design, the assembly. And it was, I know it was not easy. Also we had Azura who left, so it was not easy for you at the time. And then with Romain and me, sometimes you receive conflicting guidelines, as is often the case with multiple supervisors. And sometimes even between Romain and myself, we discuss a lot about the best way forward. So you did really great to navigate all of this. And the end result is really great. Yeah, I would like also to thank Romain and Azura for the supervision. I think it's really a team effort that has enabled this work, and you are really the central part of it. And also I would like to thank Gert, our lab expert, who saved us many times from big issues. So it was also great for me, and I'm quite proud of how you progressed during this PhD, and then you became like a peer, right? And we had, during especially the last 2 years, we had great discussions, technical discussion together, and it was very, very positive to the team. So I must admit that I failed you on one point, is that I did not manage to make you try a Belgian beer. Yeah. I have another Belgian specialty for you, right? And you tell us whether it's better than the Swiss one. Okay?
Germain, félicitations, congratulations. Again, this is for you the last part of a long journey. I think what was for all of us actually a very important adventure. I think it was great for us to have you on board, because as like so many different things became more complicated than expected, we could count on you to turn things that look to us like a lot of work into something that you made look easy, and other things that we knew would be very complicated. You managed to turn them into a success. And I guess maybe, hopefully, other people who will work with you in the future will see you turn something that seems impossible into a reality. That's what I can wish for you in the future. Yeah. So. It was very good to have you on board for all of these reasons, and yeah, to help us do all of these complicated things. I also have a little gift for you. In science, we don't often really talk in terms of symbols. We leave that to art in most cases. But the thing I have for you is here. It's, I think, a symbol that I'm hoping we have a little bit in common, and something that you'll be able to appreciate for this. So this, if you like, just go ahead and open it.
Yeah, I need to open it.
Yeah. So I think a lot of people will not recognize this, but I hope you will, because to me this is just a symbol of scientific curiosity, and keeping your sight on your scientific curiosity, and having it bring you to new frontiers, and keeping you both grounded and knowing where you want to go. And yeah, that's something that I wish for you.
Nicely chosen. Yes. Thank you. I wish I had time to prepare a speech, but I didn't. So I will try to not forget anything. So first of all, thank you very much for giving me the opportunity to carry on this PhD, and for all the amazing years of research here in Leuven. So as I wrote in the acknowledgement, They were, I think, the 4 best years of my life so far. And I think it's mainly thanks to your supervision and your management that was giving me a lot of freedom. You were giving me guidance, but also a lot of freedom to experiment and to try. And they made it into a very pleasant PhD. And I really appreciated that despite your busy schedule, you were always here to help me, always here to answer my messages as soon as possible. So I consider myself very lucky that I got you and you two and Azzurra as supervisors. I also want to thank Geert also, because so many help in the lab, that was thanks to you. So that was like very, very helpful. So in a way, you were also a bit my supervisor when I was working in the lab. Thank you, Jean-Philippe. And I hope you also say thank you to Germain from me, because as you said, I was feeling a bit alone at the engineering school, being the only one who wanted to go for astronomy. And everyone I was speaking about this to was telling me that it was nonsense to pursue this kind of career. But I feel so glad that you gave me this opportunity to work with you in this master thesis. And it's thanks to you that I'm standing here today, and thanks to you and Guillermo. So thank you a lot for all this. Thank you to all my friends who came here, sometimes from very far away, to support me and help me during the 4 years. So thank you a lot to all of you. Et merci à ma famille, à mes amis qui sont venus, qui ont pris le temps de venir me voir. C'est très... Merci beaucoup. Okay, and I think we can go to the reception. I obviously have gifts for you that I'm giving you now. I almost forgot about it. My God. This is... I will try not to break anything. This is for you, and this is for you. There is more of it in my office, but I couldn't bring all of it, so you'll have to come and collect it. And I have for the rest of the jury some gifts. It's not much, but thank you. Thank you. And that's it. We can go.